So in the previous class, we have started the number systems and their conversions. Okay. So in this particular class, we'll solve some more questions related to the number system conversions, and then how to find out the base of a number system, or how to find out the equivalent value of a particular number system. Okay, we'll solve some questions related to those concepts, and then we'll discuss about basic arithmetic operations like addition and subtraction, and then we'll discuss about data representation or representation of numbers in binary. Okay, so how we can represent various numbers in the binary format, we'll discuss here. So in this particular session, we'll cover all these topics. The binary number 100,110 is numerically equivalent to. He has given the four statements like this. First one is 26 base 16. Second one is 36 base 10. Third one is 46 base 8. And fourth one is 212 base 4. Choose the correct answer. Here he has given the binary number. This binary number is equivalent to, like this, he has given the four statements. One number he has given hexadecimal form, another number in decimal format, another number in octal, another number in base 4. Okay, he has given the four choices like this. By observing the choices, among the four statements, three are the correct. That means three numbers among the four are equivalent to this binary number. You have to find out the correct answer. 3, 4 and 1. See here, he has given the binary number, right? If you do the group of 4 bits, you will get the hexadecimal digits, right? So first I am considering 100,110. Now do the grouping of 4 bits. Here you can place 2 zeros. Okay, 0010 is nothing but 2. 0110 is nothing but 6. 26 base 16. That means first statement is correct. Once if you got the hexadecimal number, from this you will get the equivalent number in the decimal, right? So here I am considering 26 base 16. Okay, here positional weights are 16 power 0, 16 power 1. Multiply each digit with the respective positional weight and then add. 16 into 2 plus 6. 32 plus 6 is 38. This is the decimal number. But here he has given 36 base 10. That means this second statement is wrong. So the moment you found out second statement is wrong, so just observe the options. Wherever options contain second statement, all those are wrong. Okay, that means option C is the correct one. 3, 4 and 1. Now let us see whether these two are equivalent to this number or not. Let us see. Here he has given the octal number. Okay, consider the given number, binary number. Do the grouping of 3 bits. 100,110. Do the grouping of 3 bits, you will get the corresponding octal digits. 100 is nothing but 4, 110 is nothing but 6. 46 base 8. That means third statement is correct. So in the previous class, we have discussed how to convert binary number into hexadecimal octal. Similarly, hexadecimal to decimal also. Right? I haven't discussed how to convert binary number into base 4 number system. But if you observe, I have given one method or technique how to convert binary number to hexadecimal or binary number to octal. The same principle we can apply for here also. Here 8 is nothing but 2 cube. That means by doing the grouping of 3 bits, we will get the corresponding octal digits. Right? Similarly here 16 is nothing but 2 power 4. Right? By doing the grouping of 4 bits of binary number, we will get the corresponding hexadecimal digits. Similarly here 4 is nothing but 2 square. Right? So that means by doing the grouping of 2 bits, you will get the corresponding digits of base 4 number system. Right? 100,110. So here I am doing the grouping of 2 bits. 10 is nothing but 2. 01 is nothing but 1. 10 is nothing but 2. 212 base 4. Is it clear? Whatever the technique we have used for converting binary number into hexadecimal or binary number into octal, we have written 16 is nothing but in terms of 2 power 4. Similarly 8 is 2 cube. Similarly here 4 is nothing but 2 square. That means by doing the grouping of 2 bits, we will get the corresponding digits of base 4 number system. Okay, I am repeating once again. See here he has given the binary number. This binary number is equivalent to which of the following? See here he has given the 4 statements. Okay, and after this the question is choose the correct answer. That means the given binary number if you observe the 4 choices, in each choice you are having 3 statements, right? So that means among the 4 statements, 3 statements are correct. That means whatever the numbers here he has given, those are equivalent to this particular given binary number. Among 4, 3 are equivalent. 1 is wrong, right? So here he has given the binary number. That one we have converted into hexadecimal number by doing the grouping of 4 bits, right? So we got 26 base 16 is the correct answer. Here we got the hexadecimal number. Okay, from that if you put the position weights and then multiply each digit with the respective position weight and add, you will get the equivalent value, that is nothing but decimal number. Here we got 38, but here he has given 36. That means the moment you found out second statement is wrong, wherever the options contain second statement is there, all those are wrong. Similarly, you can convert binary number into octal. This one you got 46 base 8. Similarly here, 4 is nothing but 2 square. So I have done grouping of 2 bits. So I got this number. See, suppose any number he has given, suppose decimal number. If you wanted to convert into base 3, then you have to do repetitive division with 3. So that whatever the remainders you will get. In base 3, what is the digits you can represent for a single digit? 0, 1, 2. Right? So those remainders you will get. So that means you will get the digits corresponding to the base 3 number system. Like that. The same integer is expressed in different number systems. Full stop. Write down this series. He has given the series like this. Series of numbers. The missing number of the series is. Here he has given the series like this. Okay, in this series he has missed one particular number. He is asking what is this particular number. Here he has given one clue. All these numbers belong to different number systems, but all those numbers will represent same integer. Same integer. Then what is this particular number? He is asking. Okay, series means what? It will follow a particular pattern, right? So just observe here. First number. Here, if you observe the digits, here he has represented with either 0 or 1, right? So that means for the time being I am assuming this is the binary number. Actually this number will be valid in all the number systems which are having the base value greater than or equal to 2, right? For the time being I am assuming this is base 2. Okay, then I will assume this is base 3, base 4, base 5, like that. Let us see whether we are getting the same integer or not. If we are getting the same integer, that means whatever the assumption I have taken, so I will follow that particular thing. So accordingly I will get some particular base number here. So here I am assuming 1 0 0 0 0. This is the binary number. Put the position weights 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. 2 power 4 is nothing but 16. So I am getting the equivalent value 16. Now I am considering this number 1 to 1. This is base 3. Okay. 3 power 0, 3 power 1, 3 square. 3 square is 9. Plus 3 into 2 is 6. Plus 1. Equal to 16. So I am getting the same integer. Okay, I am repeating the question once again. In the following series, the same integer is expressed in different number systems. In different number systems. He has given the series like this. Okay. And after this, write down the question. The missing number of the series is. The missing number of the series is. So here he has mentioned 2 wordings. One wording is all these numbers belong to different number systems. And one more clue he has given, all these numbers represent the same integer. Okay. So here I have by the moment I observe these digits, here either 0 or 1 are present, right? So this particular number will be valid in base 2, base 3, base 4, like that. Okay, for the time being I am considering base 2. So I got the equivalent value 16. Then since he has mentioned series, so it will follow a particular pattern. Okay, so this is base 2, then base 3, base 4, like that. So here I have considered this is base 3, I got the same equivalent number. Like that, similarly you consider this is base 4, then positional weights are 4 power 0, 4 power 1, 4 square. 4 square is 16. So I am getting the same integer, right? So in this way you calculate you'll get the 16 only equivalent value. So that means this missing number belongs to base 5. This number belongs to base 5. So we have to find out this particular number. Yeah, 31 is the correct answer, right? So here, see, I am getting the equivalent value 16. That is the decimal number. I want to convert this number into base 5. That means I have to do repeated division with 5. Yesterday we have done decimal to binary, repeated division with 2. Similarly, decimal to octal, do repeated division with 8, like that. Here we are having the integer decimal number 16. We want to convert into base 5. So do repeated division with 5. 5 3s are 15, remainder is 1. 5 zeros are 0, remainder is 3. Consider the remainders in the reverse order. That means 3 1 base 5. That means the missing number is 3 1. 3 1. Just I started the series. Okay. Just the moment I have observed these particular digits 0 and 1 valid in the base 2 number system. It is valid in base 3, base 4 also. So I just started, since the minimum base is 2, I started whatever the equivalent values. Okay, I am getting, it is following. So if it is failed, then I will consider this particular number belongs to say base 3. And then this is base 4, base 5. Like that I will do trial and error. Yeah, you can consider this is base 3. But here whatever the statements he has given, it has to be valid. That means if you are starting from here 3, then this will be 4, this will be 5, like that. So whatever the equivalent values you are getting, if you are getting the equivalent integer value is same, then you can consider like that also. But here in this case it won't work like that. The base of the number system for the addition operation, 2 4 plus 1 4 equal to 4 1 to be true is. Okay, so that means whatever the numbers he has given, okay, that particular number belongs to some base B. I am assuming base is B. Okay, he has not given whatever the number, that number belongs to some base. Okay, he is asking in order to validate this particular condition, whatever the addition operation he has given, in order to validate that particular relation, what is the base? We have to find out that particular base. So here, whenever we are finding the equivalent value, what we are doing, whatever the base is there, we are putting the positional weights in terms of, in powers of that particular base, right? Here, that base we are assuming as B. So that means here positional weights are B power 0, B power 1. Okay. So multiply each digit with the respective positional weight and then add 2B plus 4 plus B plus 4 equal to 4B plus 1. 2B plus B is 3B. 4 plus 4 is 8 equal to 4B plus 1. 4B minus 3B is B. 8 minus 1 is 7. So in this case we got single root, that is B equal to 7. Suppose if you are getting two roots, okay, then which root we have to consider? Since here we are getting single root, that is the valid answer. But in general, you may get sometime two roots. Suppose if you are having some quadratic equation, that time you will get two roots. So which root I have to choose? Yeah, positive root, suppose. Okay, suppose even if you are getting two positive roots, among the given digits, okay, here all these numbers belong to base B. I am assuming base B, right? So here just find out what is the maximum digit he has given. Here maximum digit is 4, here also maximum digit is 4, here also 4. So among all the numbers, the maximum digit he has represented is 4. That means the base B should be greater than or equal to maximum value of a single digit plus 1. Base B should be greater than or equal to maximum value of a single digit plus 1. Okay, now substitute. Here the maximum value he has represented is for a single digit, that is 4. So B is greater than or equal to 4 plus 1. So that implies B is greater than or equal to 5. So whatever the roots you got, suppose in this case you got single root, that particular root, it is satisfying this particular relation. That's why it is the correct answer. Suppose if you are getting two positive roots, among those, whichever root is satisfying this particular relation, that will be the correct answer. So for all these type of questions, this particular relation will be there inherently. He never mentioned anywhere related to this base condition or relation. Okay, we have to drag that particular relation. Okay, this is very important formula. You can put in the box. This is very important formula. Yeah, this particular relation will be applicable for any number system. Suppose just like in decimal number system, what is the maximum value you can represent? 9, right? So 9 plus 1 is 10. Base B should be greater than or equal to maximum value of a single digit plus 1. This is very important formula. For this kind of questions, we have to use this particular relation in order to get some relation. Okay. If you don't use this relation, then whatever the solutions we are getting, okay, that may be correct or may not be correct. See, theoretically you may get some roots because you are having some quadratic equation. But whatever the roots which are satisfying this particular relation, that will be the correct answer, like that. Because see here, in this case, 7 is there. Okay, actually you can represent. See, the moment if you found out, see here, maximum digit here has represented for a single digit is 4. That means whatever the given numbers will be valid in base 5, base 6, base 7, like that, right? But this particular addition operation will be valid in this case for only one root, b equal to 7. That is satisfying this particular relation also, like that. Okay, we'll discuss related to quadratic equation, that questions also. He will give some number, okay, if you are having 3 digits, then if you put position weights b power 0, b power 1, b square, then you will get the equation in the form of quadratic, having power 2, right, x square or something, b square plus something, like that. Okay, write on next question. If 135 base x plus 144 base x equal to 323 base x, then the value of base x is. See, maximum value of a single digit means, see, in the previous question he has given the numbers, right? Or of, I have assumed all these numbers belong to some base. Here I have assumed that base is b. Just observe individual digit. Among those digits, which value he has represented maximum. Here in this case, maximum value he has represented here 4, here also 4, here also 4. Among all, 4 is the maximum. So I have considered that value. Similarly here he has given the question, if 135 base x plus 144 base x equal to 323 base x, then the value of base x is. See here, put the position weights. Here in this case he has given base is x, right? Position weights will be x power 0, x power 1, x square. Okay. Similarly here you will get same thing. Similarly here also. Okay, now multiply each digit with the respective position weight and then add. So you will get x square plus 3x plus 5 plus x square plus 4x plus 4 equal to 3x square plus 2x plus 3. Here x square plus x square is 2x square. Then 3 plus 4 is 7, 5 plus 4 is 9, equal to 3x square plus 2x plus 3. 3 minus 2 is 1, x square, 2 minus 7 is minus 5, 3 minus 9 is minus 6. What are the roots you will get? Here you got the quadratic equation. You will get 2 roots. What are the roots? X equal to 6 and x equal to minus 1. These are the 2 roots. Now, since you are getting negative root, the moment you got the negative root, you can eliminate. This won't be the base. So obviously x equal to 6 will be the answer. But just if you observe this particular relation, base, here he has assumed x, okay, that should be greater than or equal to maximum value of a single digit plus 1. Here maximum value is 5 for a single digit. Okay, here 4, here 3. So among all, 5 is the maximum, right? So 5 plus 1. So that means x should be greater than or equal to 6. So whatever the 2 roots you got, okay, this particular root is satisfying this relation. So that's why this is the base. Here since you got negative root, straight away you can eliminate. Otherwise if you are getting positive root, okay, whatever the root you are getting, that one, if it is satisfying this particular relation, then that will be the answer. Otherwise, that won't be the answer. Okay, so for this question, answer is 6. Base is 6. Yeah, that's what I am telling. If 2 roots you are getting, positive roots, suppose. Okay, if both the roots are satisfying this particular relation, both are valid. If only one root is satisfying, that will be the answer, like that. See, we cannot represent, if we are having the base value 0 or base value negative, we cannot represent the digits. Suppose yesterday we have started, in the previous class we have started, if base value is 2, then we can represent the digits for a single digit is either 0 or 1, right? If base is negative, then how we can represent for a single digit? It's not possible. the base or radix of the number system such that the following equation holds is. He has given the equation like this: 312 divided by 20 equal to 13.1. Holds is means that particular relation will be valid or true. That is the meaning. Here he has given the equation like this. He is asking the base of this particular number system. Here you can assume the given number belongs to, say, base B. Okay. So now here position weights are B power 0, B power 1, B square. Here position weights are B power 0, B power 1. What about this one? Here position weights will be, here B power 0, B power 1, here it will be B power minus 1. Here position weights are B power 0, B power 1, B square. Here position weights are B power 0, B power 1. Here B power 0, B power 1. Here B power minus 1. Multiply each digit with the respective position weight and add. 3B square plus B plus 2 divided by 2B plus 0 equal to B plus 3 plus 1 by B. B power minus 1 I can write it as 1 by B. Do simplification. 3B square plus B plus 2 divided by 2B equal to, here LCM is B, B square plus 3B plus 1. B will get cancelled. Here you will get 3B square plus B plus 2 equal to 2B square plus 6B plus 2. 2 will get cancelled. 3B square minus 2B square is B square. B minus 6B is minus 5B equal to 0. From this you will get two roots. B equal to 0, B equal to 5. Here B equal to 0 won't satisfy this relation. And anyway, since it is the 0, we can straight away eliminate. So answer will be B equal to 5. Here among the given digits, okay, if you observe the maximum digit is 3. Here also maximum digit is 3. That means base value should be greater than or equal to 3 plus 1. That means B should be greater than or equal to 4. So only B equal to 5 will satisfy this relation. So answer is 5. Base is 5. Next question. Consider the equation 1, 2, 3 base 5 equal to x8 base y with x and y as unknown. The number of possible solutions is dash. He has given the equation like this: 1, 2, 3 base 5 equal to x8 base y. Okay, and he is asking the number of possible solutions. See, here base is 5, so you can put position weights as 5 power 0, 5 power 1, 5 square. Here base is y, put the position weights as y power 0, y power 1. Multiply each digit with the respective position weight and then add. So here you will get 25 plus 5 into 2 is 10 plus 3 equal to xy plus 8. 25 plus 10 is 35 plus 3 is 38. 38 equal to xy plus 8. So from this you will get xy equal to 30. So here you can consider either y values and you can find out the corresponding x values in order to satisfy this relation, or you can assume x values and you can find out the corresponding y values. Okay, here you can choose either of the thing. Okay, for the time being I am considering y values and I will find out the corresponding x values. See here, if I consider y value is 1, then x value will be 30, y value is 2, x value is 15. 3 tens are 30, 4 not possible, then 5, 6 are 30, then 6, 5. So repeat: 10, 3, 15, 2, 30, 1. So just you can consider either x value and you can find out the corresponding y value, or you can consider y value, you can find out the corresponding x value for this question, because here you can assume either of the thing. Okay, so here total you got 8 solutions, but 8 is not the correct answer. Here you got 8 relations or 8 solutions are satisfying this particular relation, right? But as I mentioned earlier, I have given one formula. Just observe here, base is y, okay, x we don't know, right? So among the given digits, known digits, 8. So here we are having only one known digit, that is 8. So you can consider that is the maximum value. Okay. So y should be greater than or equal to maximum value of a single digit plus 1. So that means 8 plus 1. So that means y should be greater than or equal to 9. So now whatever the y values you have considered, okay, whichever values are satisfying this particular relation, y should be greater than or equal to 9. That means only 3 solutions. Only 3 solutions. Okay, so answer is 3. See here, very simple. Just observe here, y is 10, x is 3. 3, 8, base 10. That is possible. In the decimal number system, you can represent the digits 3, 8. Next, if you consider y value 15, here x value is 2. 2, 8, base 15. That is also possible. Then 30, base 30, x value is 1. 1, 8. That is also possible. Suppose if you consider here 6 and here 5. See, if you are having base value 6, here 5, that is okay, but here you are having 8, right? So that is not possible. When you are having base value say 6, you cannot represent digit value 8 in the corresponding number system, right? So that's why practically we cannot represent. See, theoretically you are getting the solutions, but regarding base we cannot represent with these solutions. That's why answer is 3. See here, base value is y related to x. What is the relation? X value should be starting from 0 to y minus 1. Within this range you can consider x values from this. Or you can say x is less than y. Here base is y, whatever, here x is nothing but digit value, right? That should be less than the base. Since we don't know regarding x, in the question he has mentioned x and y are unknown. Okay, we don't know whether it is a maximum more than this or not, we don't know. See here you got, suppose here you got say x is 30. Okay, 30 is greater than 8. But here y should be what? If x you are considering 30, then y should be, obviously minimum value is 31, like that. Minimum value. Or y should be greater than 30, like that. But here what are the solutions you are getting? These solutions won't satisfy. You cannot represent a number with these solutions, these 5 solutions. Only 3 solutions are satisfying here. Here, digit value will always be less than the base. Just like in the decimal number system we are having base value 10, we can represent the values ranging from 0 to 9 for a single digit. Similar question, consider this equation. 4,3 base x equal to y3 base 8. You have to find out the number of possible solutions. Similar to this question. Same question but different equation. You have to find out the number of possible solutions. Try to find out the number of possible solutions here. Try to find out the number of possible solutions for this question. See here, base is x. So put the position weights x power 0, x power 1. Here base is 8, 8 power 0, 8 power 1. Okay, so here you will get the equation 4x plus 3 equal to 8y plus 3. 3 will get cancelled. So here you will get 4x equal to 8y. From this you will get x equal to 2y. X equal to 2y. In this case, you can assume y values and you can find out the corresponding x values. In the previous case, you can assume either x value or y value. But in this case, y is the independent variable whereas x is the dependent variable. You can assume y values and from that you will get the corresponding x values. Okay, so here if you observe, here base he has given 8. That means octal number system. Okay, here the digit values will be what? Ranging from 0 to 7. If you know the base value 8, that is octal number system, right? The digits you can represent is 0 to 7. Okay, now x value is nothing but double of y. Okay, just double it. Now, here among the given digits, maximum value is 4, right? So the base x should be greater than or equal to 4 plus 1. That is, x value should be greater than or equal to 5. X value should be greater than or equal to 5. So that means only these 5 solutions are satisfying. X values should be greater than or equal to 5. Answer is 5. See, up to here we have discussed about related to base. Base should be greater than or equal to max value of a single digit plus 1. Some people might have taken here y should be greater than or equal to 8 plus 1. That means y will be greater than or equal to 9. So that means you will get infinite solutions. Here in this case, he has given the base, okay. He has not given the digit. That digit he has represented with y. So that means the moment you know this is octal number system, base values, the digit values corresponding to that number is 0 to 7, 0 to 8 minus 1. So if you don't use this particular relation, then whatever the answer you are getting, that will be the wrong. Okay, you have to use related to the base relation. Then only you will get the correct answer. So here in this particular questions, the very important formula is related to base. Base value should be greater than or equal to max value of a single digit plus 1. Next question. The minimum number of bits that are required for representing the decimal number 6728. The minimum number of bits that are required for representing the decimal number 6728 is dash. Here he is asking the minimum number of bits that are required for representing this particular number. He has given the decimal number. Yeah, the given number is decimal number. He is asking the minimum number of bits that are required for representing this number. That means you have to convert this decimal number into binary, but it will take more number of iterations. For this question, first you can convert this particular number into hexadecimal, okay, and then whatever the hexadecimal number you got, convert into binary. Okay, after that if you are getting leftmost side zeros, you can remove because those are insignificant. Here in this question he is asking minimum number of bits. From that you will get the answer. First convert the given number into hexadecimal number. What is the hexadecimal number you are getting? Do repetitive division with 16, you will get the hexadecimal number. Or you can convert into octal also, there is no issue. You can convert either into octal or hexadecimal. From that you convert into binary. After that, if you are getting leftmost side zeros, you can remove. And then find out the remaining bits. That bits will be the answer. What is the hexadecimal number you are getting here? Do repetitive division with 16, you will get the remainders. Okay, those remainders will be corresponding to the hexadecimal digits. You have to consider in the reverse order. What are the remainders you are getting? You have to consider in the reverse order. You can check, you will get 1A48 base 16. Yeah, 1A48. You can check later, convert this decimal number into hexadecimal by doing repetitive division with 16. Okay, you will get this number. Okay, now represent each hexadecimal digit with 4 bits. 1 is nothing but 0001. Then A is nothing but 1010. 4 is nothing but 0100. 8 is nothing but 1000. After converting the hexadecimal number into binary, if you are getting leftmost side zeros, you can remove. Here 3 zeros are there, those 3 zeros you can ignore. Now, just count the number of bits. Here 4 plus 4, 8 plus 4, 12 plus 1. That means 13 bits are required. Okay, this is one method. Other method is, what you can do, since here the number is 6728. Okay, most of you people remember this particular value. What is the 2 power 10 value? That means, if you are having 10 bits, you can represent the values ranging from 0 to 1023. If you are having 10 bits, okay, the starting value is 0, right? So 0 to 1024 minus 1, that means 0 to 1023. So here the given number is larger than this, that means 10 bits are not sufficient. Multiply with 2, you will get 2 power 11, that is nothing but 2048. 0 to 2047. Still this number is larger. Multiply with 2, 4096. 0 to 4095. Still this number is larger, that means 12 bits are not sufficient. So take, multiply with 2, you will get 2 power 13. That is nothing but 8192. So you will get 0 to 8191. So if you are having 13 bits, you can represent the values ranging from 0 to 8191. So this number is falling under this particular range. So that means the minimum number of bits required is 13. If you are having 13 bits, the max value you can represent is 8191. Okay, if you are having 12 bits, max value you can represent is 4095. But here 6728 is greater than 4095. So that means 12 bits are not sufficient. So answer is 13. Okay, I am repeating once again. Most of the people will remember this particular number. 2 power 10 is nothing but 1024. See, for example, suppose you are having two single bits. Okay, if you are having two single bits, you can represent 0 0 0 1 1 0 1 1. These are the four combinations, right? So here bit position value is 2 power 0, here bit position value is 2 power 1. So multiply each digit with the respective position weight and add, you get the equivalent value, right? Here both the bits are 0, equivalent value is 0. Here 1 is there, 1. Here 1 under position weight 2. Here 2 plus 1, that is 3. So if you are having two bits, we can represent, see what are the equivalent values you are getting, those are the decimal numbers, right? So if you are having two bits, you can represent the values ranging from 0 to 3. 0 to 3. Okay, so here what is happening? I am having two bits, that means 2 square. Okay, that should satisfy, that should be greater than whatever the equivalent value you are getting. So I am assuming this particular number is say n, whatever the decimal number. Okay, so here if you are having within this 0 to 3, you can, if you are having two bits, you can represent. See, suppose if you are having single bit, okay, here I can give the generalized formula like this: 2 power n greater than n, where small n is the number of bits and capital N is the decimal number. Capital N is the decimal number. Suppose here I am considering decimal number 3. Okay, for representing, see, if you are having a single bit, you can represent that bit with either 0 or 1. That means equivalent value you will get 0 or 1, right? So that means if you are having a single bit, you can represent either 0 or 1. The equivalent value also same, 0 or 1. But if you are having the decimal number 2, you cannot represent with a single bit. Okay, so here you require two bits. Okay, so if you are having two bits, you can represent the decimal equivalent numbers is 2 and 3, like that. So that means if you are having two bits, okay, total you will get 4 combinations, right? 2 square is nothing but 4. Okay, 4 minus 1 is 3. That means starting from 0 up to 3, we can represent with 2 bits. That is the meaning. Similarly here, if you are having 10 bits, 2 power 10 is nothing but 1024. Okay, so that means with 10 bits we can represent the bits in terms of zeros and ones. The corresponding equivalent decimal numbers you will get 0 to 1023. 1024 minus 1. Okay, but this particular number is greater than this one, right? So that means 10 bits are not sufficient. So that's why I am multiplying with 2. I am getting 2 power 11. 2 power 11 is nothing but 2048. Okay, so here we can represent the corresponding decimal numbers as 0 to 2048 minus 1, that is 2047. Okay, still this number is greater than this. That means 11 bits are not sufficient. Like that I am continuing the process till whatever the given number is falling in which particular range, so that particular corresponding number of bits I am taking, because the question is minimum number of bits. Okay, so this particular question you can use this particular relation also. That means 2 power n greater than the given number, that is 6728. Apply logarithm on both sides, so you will get n log 2 base 10 greater than log 6728 base 10. From this you will get n value should be greater than log 6728 base 10 divided by log 2. Log 2 is 0.3010. Just simplify this one. What is the number you are getting? N greater than 12.7. Okay, so consider the nearest integer, that is n equal to 13. That means we require 13 bits. We don't have 1/4 bit or 0.2, 0.5 bit like that, right? So we have to take the nearest integer. With 12 bits we cannot represent. So what are the condition is this particular relation satisfying? Take the nearest integer. N value 13. That means 13 bits are required. Okay, so next question, just consider this is the decimal number 4095. Convert this number into hexadecimal, and the moment you got the hexadecimal number, okay, represent each hexadecimal digit with 4 bits. You will get the binary number. And then do the grouping of 3 bits, you will get the octal number. Consider this decimal number, convert this one into hexadecimal first. Do the repeated division with 16. Okay, here you will get the hexadecimal number, represent each digit with the 4 bits. You will get the binary number. And then do the grouping of 3 bits, you will get the octal number. Here my intention is not to convert decimal number into binary. Here I want to give the conclusion. In the earlier class I have mentioned, in our daily life we are using decimal number system, right? Computers or digital circuits operate with binary numbers, Okay, apart from these two, we are considering octal and hexadecimal. I want to give the conclusion based upon this question. So first you can convert the decimal number into hexadecimal or octal. Whichever method you are comfortable, you can follow. And then you convert that number into binary and then you convert into other number like that. Yeah, triple F, right. So now you can represent each digit with the 4 bits. F is nothing but 4 ones. Okay, now you do the grouping of 3 bits, you'll get the corresponding octal digits. Okay, someone is asking decimal to hexadecimal conversion. Okay, let us see. 4095, this is the decimal number. Okay, so here we have to do repetitive division with 16 in order to get the corresponding hexadecimal digits. 16 2s are 32, remainder is 8. So here you are having 89. 16 5s are 80. Here remainder is 9. 95. 16 5s are 80. So remainder is 15. 15 is nothing but F. 16 2s are 32. Remainder is 8. So here you are having 89. 16 5s are 80. Remainder is 9. 95 I am having. 16 5s are 80. So remainder is 15. 15 is nothing but F. 16 1s are 16. Remainder is 9. 95. 16 5s are 80. Remainder is 15. That is nothing but F. 16 zeros are 0. Remainder is 15. That is nothing but F. So here we'll get triple F. So here just observe. Here number of digits is how much? How many digits are there? Number of digits. Here number of digits is 3. Here number of digits is 12. Here number of digits is 4. Okay, just observe. We are having 4-digit decimal number. When we are converting into binary, we are having 12 digits. 12 binary digits is nothing but 12 bits. Okay, so here I am having 12 digits. Okay, here I am having 8. Here I am having 16. See, whenever the users or programmers, two programmers are dealing about this particular binary number. Okay, so whenever they are supposed to talk about this particular binary number, here they are having 12 ones, right? 12 digits they are having for a 4-digit decimal number, right? So whenever they want to write or whenever they want to speak about this particular number, it is having more number of digits. Here I am having 4 digits, but here I am having 3 times more. 4 3s are 12, right? So that's why, see, internally all the circuits will operate with binary numbers only. Whenever you are giving the decimal number, internally the digital circuits will operate with binary numbers, that is in terms of ones and zeros. But whenever the users or the programmers want to deal about this particular binary numbers, then for them it is easy to write or easy to say if they can use either hexadecimal or octal, right? Here if you do the grouping of 3 bits, you will get the corresponding octal digits. If you do the grouping of 4 bits, you will get the hexadecimal. Okay, here you are having number of digits is 4, that is same as here number of digits in decimal 4. Okay, but when compared to this one, still here you are having 1 digit lesser, right? So among these two, this is the recommended. Hexadecimal number system is recommended. Okay, so some people wrongly think like the circuits will operate with octal number system or hexadecimal. Not like that. Internally, all the digital circuits will operate with binary numbers only. Suppose here I am having all ones, so I can say directly 12 ones. But if you are having in combination of ones and zeros, it is difficult to pronounce or difficult to say to other user or programmer. That's why here will represent whatever the binary number I am having, that one will represent either in terms of octal or hexadecimal. Among these two, this is the recommended. See, very simple. All the digital circuits internally will operate with binary numbers in terms of zeros and ones only. Okay, so that's why whatever the decimal number you are entering, that one will convert into binary. So internally the circuit or microprocessor will operate in terms of binary numbers only. Okay, after that, whatever the resultant binary number you got, that one will convert into decimal, like that. But whenever the users or programmers want to deal about binary number representation, okay, for them it is difficult to write or read if you are having more number of bits. See, here 4095, you are having 4 digits, directly you can say 4095. Okay, here I am having 12 bits are 1, but if it is combination of suppose ones and zeros, then it is difficult to pronounce, or that many number of digits write is also very difficult. So that's why for representing that binary number, they will use either octal or hexadecimal equivalently. Because here you are having number of digits is 3, here number of digits is 4. Among these, this is the recommended.